Hi guys. Um, so in this video, we are continuing on discussing the compressive joint. So in this second video, we take a look on concentrated loads in bearings. So concentrated load, as the name implies, so when you have a plate smaller than the supporting members, so the dimension of the applied uh, loading platen, PP over HP, PP or HP, this one, the plate here, are smaller than the dimensions of the supporting member of BP. So here's BP. So this is your supporting members, for example, column, core bear, and so on. So the distribution of compressive stress across the section is uniform. It is uniform up until the point here, and then it started to increase, disperse. So the distance is known as the characteristic length, LE here. So this is your characteristic length. So this distance depends on the Poisson ratio. The value for concrete is 0.2, and then on the ratio of BP over B and HP over H. The width of plate to the width of the supporting members, also the length of plate over the length of the supporting member. You can see here. So as a general rule, characteristic length LE is equal to B or H. So the change in stress within this region, the gradient curve of the stress curves in 8.7 give rise to shear stress. You can see it gives rise to the shear stress because the force is propagated along the trajectory, and it gives rise to the shear stress on the concrete. So also causes lateral expansion due to the trajectory of forces, which depends on the V, depends on the Poisson ratio of the concrete, and then produces lateral tension in the concrete, commencing at about at about Y over B, 0.15 to 0.2, the ratio of 0.15 to 0.2. So let's say your B is 200, so it commences about uh, 40 mm, 40 mm from the top until the 200 length, and extended for distance about y is equal to 1.2 b. If your b is 200, then it extends to 2.4. So lateral tension stress is greatly influenced by the ratio bp over b and distance from the bearing pad. So the stress, the lateral tension stress, depends on the ratio of your plate to supporting members with, and then the distance from the bearing pad. You can see here the distance from the bearing pad. So this is your bearing pad, this is your A, this is your D members, and this is your B. So in the case of bearing plate, BP over BP times HP embedded in the section BH supporting members, allowable bearing stress FB is given as this equation. So you have 0.6 times your concrete compressive strength, and then your dimension for supporting members and dimension for the plate. It should be less than 2 times your concrete compressive strength. So in design, the lateral stress in figure 8.8 is integrated to give lateral tensile force, which must either be resisted by the tensile strength of the concrete or by reinforcement in the form of closed link in the region of 0.1 to 1.0, in region of, if your B is 200, then it's in the region between 0.2 to 200. The if it is your B is 200, then the region is between 20, 200 times 0.1, 20, and 20 to 200. 300, if your width is 300, then 30 mm to 300 mm. So the ratio of the lateral bursting force, known as FBST, F bursting, to the applied force F is called the lateral bursting coefficient. So this coefficient will convert your axial force, vertical force, to bursting force to calculate your bursting length. So in BS, British Standard 8110 Part 1, Table 4.7 gives the value for the bursting coefficient in terms of a 2D ratio of YPO over YO, where YPO is a half of your plate, and YO is a half of the block, the supporting members. So whichever the least, if B is smaller than H, then B should be taken as B over 2 should be taken as YO, BP. If BP is smaller than HP, and BP over 2 is taken as YPO. So basically, when you have your BP over B or HP over H, whichever the least, so the ratio determines the value of your bursting coefficient. If it is less than 0.3, then it'll be 0.23. The contribution of the ratio of bursting coefficient. So basically, as you can see here, as your ratio becomes smaller, the value become higher. So the contribution of vertical force to bursting force becomes higher. If your plate, so basically, if your plate become larger, your BP is larger, divided by a smaller B. For example, your BP is 100, your B is 200, so the ratio is 0.5. You get the contribution is 0.17, 17%. 17% of the force from the vertical is transformed into bursting force. So smaller compared to if your value is 0.3, for example, your let's say your B is 1000 and your BP plate is 300. So 300 to 1000 is 0.3. So the coefficient will be larger. So basically you're transforming more of your axial force towards the bursting force. Depends on your members, depends on your components you are using. But there are solutions for everything. So if your bursting coefficient is high, then you need to design for a higher number of steel area. So let's take a look at the example here. So the example say calculate the maximum concentrated load, the maximum V to be applied on this 200 times 300 concrete block, which is this is your supporting members, supporting components, through a steel plate. So you have a steel plate. So the load is applied on the plate, then onto the concrete block. So calculate the minimum lateral bursting force, and choose suitable bursting reinforcement, and then design your bursting reinforcement. You need to use your concrete grade 40 and your high steel, high high strength steel of 460 Newton per millimeter square. So the solution, this as given the question, your dimension is 200 times 300. So let's say your 200 is B and 300 is your length H. So BH supporting a plate, and then what is the force here? Maximum applied. So to know the allowable bearing force, need to use equation 8.3. So this is equation for 8.3. This is your FCU basically. This is also your FCU. This is your B. This is your H. and you want to find the dimension of the plate lah, because it is not given in the question. So basically the maximum allowable bearing will be equal or less than 2 times 40, 2 times FCU. So in this case, it is should be less or equal to 80. So you solve for this one, or go to the right hand side. So you get your value of BP times HP, as in this example. So your value of HP times BP is 5400 millimeter squared. So to ensure that the minimum bursting ratio is found, so your HP over BP should be equal to the ratio of your supporting members. This is your supporting member, the block here. The block here, 2 times 200 times 300. So the ratio is HP H to B is equal to 1.5 lah. So in that case, 1.5, you convert this 1.5 from this 4500. So you propose that the dimension is 90 times 60. As you can check back here, 90 over 60 is equal to 1.5. So the ratio is similar lah. So you get the least would be BP, and also HB, B here. So BP over B. um, so based on this, you can get your maximum allowable bearing force, which is based on this 2 times FCU times with the area of your plate. So that is your allowable maximum allowable bearing force, which is 432 kilonewton. And then we want to calculate how much is the bursting force, FBST. So for that to happen, you need to calculate your ratio of BP over B or HB over H, which is 0.3. So 60, this is 90 over 300, and this is 60 over 200. So both values will give you 0.3. So check back from table 8.1, you can see that if it is 0.3 or less, then your bursting coefficient will be 0.23. So by using 0.23, you convert, multiply. So basically 432, 23% of 432 will be converted, is uh, will be bursting forces, which is the 99.4 kilonewton. So using equation 8.4, area of steel. So using equation 8.4, area of steel. So 8.4, where you have your bursting coefficient, which is basically uh, F over P, F over P, then you get E lah. Basically P ataupun this is a Young modulus E. But the value of allowable stress is based on the code, should be 95%. We reserve that 5% for any uh, abnormalities or any error during construction. Basically F over P. So your F is here, 99.4 divided by your 0.95, and then your 460 Fy is given here. Fy. So you get your area of steel that is required. So based on that, you can propose to use three numbers of T10. You can see here, based on the T10, your area of steel will be higher than the required area of bursting. So you provide links. You provide three numbers of T10 links distributed from 220 to 200 mm, which is 0.1 to 1.0 B, based on your B. This is a specification where you can put your bursting reinforcement or inside your block. So there will be one steel here, and another steel distributed up until 200 mm. So this is table 8.1. You can check and try to do it yourself. And I see you in the next video, for example 8.4.